Welcome to today's edition of Calculus in the PM. I'm your host, Mr. Shindaki. 2.4 rates of change tangent lines. We're really starting to get into this will change the rest of your life. Today is the first day of the rest of your life, by the way. Anyways. Every day it renews itself, yes. Anyways, tangent lines. This is moving towards something we call derivatives, which you'll be sick of come January. Rates of change tangent lines. Let's just read this carefully and think about this. A tangent line to a curve at a point P is the limiting position of a sequence of secant lines drawn through P and Q. As Q approaches P, provided the limiting position is the same, no matter if Q approaches from the left or the right, approaches P. Well, that was a mouthful. What am I talking about? Okay, let's stop and think here. So here's my point P. Do you guys, first of all, you guys talk tangent lines a little bit? Sometimes people tell me in words, what's a tangent line? Oh, come on. Yeah, it kind of touches once and only once is what people often say. Kind of. That it can't pass through something, and it might, okay. But this would be non-straight, but it's an approximation of the tangent line there. You guys familiar with that? So how do we come up with the actual tangent line is what we're wondering. There has to be a formal method, though, because I do this when I teach physics and stuff like this. I will get people to do tangent lines on graphs to determine instantaneous velocities and stuff like that. And what happens is that I will draw it like this. It'll be pretty good. You will draw it just a slight bit off. It'll still look like it's touching once and only once, but it's imprecise, right? You won't repeatedly get the same. The slope of that line will be slightly different. So you have to have a method that gives you the same answer every time. So if we use this method, we say a secant line. Now a secant cuts, basically. You guys probably talked about secants and chords in grade 9 a little bit in math, right? Did you guys talk about a secant being that? It cuts twice, it hits the circle twice? Okay, sometimes that, for time reasons, sometimes that chapter is overlooked, and it's fine. But that's called a secant there. A secant line, this would be going back, if you've seen it, it would be grade 9. So, if you haven't, you haven't, and it's no big loss. So a tangent line to a curve at a point P is really the end result if you take secant lines drawn through points P and Q. Now here's P and Q. Now if I draw the secant line, and I'm going to draw it and disappearing naked. Okay, here's one. Now if I take that slope, okay, I could write that down somewhere. Then apparently, as Q approaches P, I say, right? As Q approaches P, so I move it in a little closer, right? Now this is going to be closer to what the actual tangent line is. Right? That makes, okay. Now as Q approaches P, so I move Q in closer here. And then I draw the secant line. Now, the reason why I need 2 points is, how do you find a slope between 2 points, right? And when you do it, you need a point P and you need a point Q. And this is why you keep moving this closer and closer. Do you remember how at the very start of this chapter we talked about this little distance in between things called H? It's getting closer to 0. Well, the idea is that you move Q closer and closer and closer until basically they're overlapped on each other. Now, you can't truly have it sitting on top, because if they have the same x value, you're dividing by 0, right? So it still has to be some infinitesimal small distance away. But do you agree that the slope of this, what I have here, P and Q right here, if I draw that, that's going to be basically this, approaching the same result from the left or the right if I draw this tangent line, right? Now, I'm not being very careful when I'm drawing my tangent lines, but you imagine that whether I approach from the left or the right, I get the same value for the slope. that must be the same line. So, now, there we are. I just had this here, because I had some kind of Q value there or something like that. That's what this is talking about. Now, do you understand this sentence there? It takes a while to understand what we're talking about. Okay. By the way, finding the average rate of change is finding the slope of a line between P and Q. And we know the slope formula, right? Y over x minus x. Okay. Except that we're getting to the point now where we're less reliant on using y as a variable all the time. So in function notation, that's the function with the q values x put in, f of the p values x put in, right? And that's what this, you see how it's the same formula, the slope. That wasp didn't wake up, did it? Okay. Okay, good. If you scream, I know why. 6 demerits. Okay. You could see that from the left to the right you'd get the same value, but do you see how we'd run into a problem? If the function has a cusp or a kink in it. A cusp is sort of like the official name or whatever, but this kind of a shape. Why? Because, well, just take a look. From the left and from the right, do you get the same value? Well, here I'm getting something that's very steep, but increasing from left to right. From this side, if I had q on that side, you see you get a negative value. You will not get the same slope. As a matter of fact, if you think of the tangent as a freehand drawn thing, at a point like this, you could draw it here, you could draw it here as well. That way sure doesn't work, but when you use the definition as it approaches from the left or from the right, I don't get the same value, do I? So a tangent line doesn't exist at a point P if that point is on a cusp, a corner. You could say that too, right? Okay? So that's something to first arrive at. We need smooth functions. We'll call them differentiable later, but okay? So, estimating the slope of a tangent line. Use a chart to estimate the slope. When x squared is, okay, I've got this graph here. I've done the graph for x squared minus 3. That's not a mystery, though, but whatever here. When x equals -1. So I've got the tangent line drawn there, right? You can see. That's a pretty good estimate of the tangent line. Now, how do I do this, though? Well, I'm going to do it by chart. Find the slope of P and Q. And I don't have a Q on here. Why? Because Q keeps moving. First I'll put it here. First up, then there, 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 and then I'll move it really close. Why would I start so far away, though? I'm not going to use 3. I'll start right down at 0, maybe, and come in. And then I'll do it from the left side. So I didn't draw in Q on that diagram because it keeps moving, right? Do you understand what I mean by Q is the second point for each different Q value? This first calculation finds the average rate of change for this function. Well, let's look at this chart. Okay, and then we'll come back to that. Here's my point. Point P is always going to be this -1, -2. Where did I come up with -2? From that function, x squared minus 3, right? So I plugged in -1, and that's how that came up. So you got that there, right? Now, my y values, and I know I'm using y talk always because I know that's what we're used to saying. My function values, they're going to be in this column. These are all the x values. Now, every time we're doing the slope between this point, so -1, -2, and a q value, and it keeps changing. Well, let's go through this one together. I have the work here, but so I'm saying if we have a q value at -2, we have a y value here. You see that's the first q1 right up there, right? So if we do this slope between here and here, I didn't draw it that great. We take the slope y minus y, so -2 minus 1. You guys see where those came from? I'm just doing the slope form. And then, of course, x minus the other x value. That's what this negative 3 came from. And that's what I'm explaining here. This first calculation finds the average rate of change for this function, f of x squared, f of x equals x squared minus 3, on the interval from -2 to -1. You guys follow that too? So if I ask for the average value of rate of change, use the slope form. I've done the second one for you. Keeping in mind that it's still from point P, and this time 0 and 3, this point to this point. So it's x minus x, or y minus y over x minus x, right? -2 minus -3, that's where they came from. And then the x values. -1 minus the 0. You all good with that? You guys have calculators. I'll get you to do these. Whether you want to take the time to put this equation into your calculator, I'd suggest it as y1, x squared minus 3. Come up with your y values that correspond here and so on. And then use your calculator, come up with your slope. I'll let you do this. I'm going to pause the video, but I'll let you do this. After doing some calculations, you arrive at the conclusion, looking at the trend, probably -2. The slope of the tangent line is -2. Seems logical. But, as I mentioned here, there's got to be a better way. But if you have a computer program and stuff to analyze stuff, you would actually probably program it this way, not using a function, but just using like a set of values. Right? Okay. And you could derive at that kind of stuff. So what do we got to do? I said there's got to be a better way. There is. And we'll learn how to do this without using a chart. The chart is one method if you're ever asked, though. And sometimes, if you don't know how to work with a function intentionally, you might be given something like that. And in AP classes, as you know, I've told you that functions will be represented by graphs, the actual functions themselves, or sometimes charts without the actual like x squared plus whatever given. So be prepared with estimating slopes of tangent lines using graphs. Later on we'll call that derivatives estimating and stuff like that. Okay, estimating the slope of a tangent line without a chart. So, hey, I've used the same one. Okay, we did this one with the chart, didn't we? So, when x equals -1. So what do we got to do? We got to create or imagine a secant line. I have the drawing down here. So, very much like we did at the start of the chapter when we introduced this idea. P here, that's locked in. You girls okay? Q is this point that I keep moving, right? And I'm going to have it this distance h, x distance away from P. H will get smaller and smaller in this argument. Like you'd move Q closer and closer and closer until it's finally practically on top of P. But Q, we'll say, is close to -1, but it's got this little extra distance, plus h, put into it. You guys get that idea? We kind of saw this before. If you're not quite sure, go for the ride and just go through this example and then see what happens. So, and then the y value that corresponds to -1 plus h is the function plugged in. Not close to anyone the wasp is fine?
He's still up there.
He's up there. Okay, good. So, the coordinates of P are -1 and -2. We know how you find that. Q, well, the x is I guess not going to is. I'm going to put equal. Sorry, I'm still distracted with this wasp here. -1 plus h. y is negative 1 plus h, plugged into the function. What was the function? It was x squared minus 3. That was given to us for this problem only, right? So I'm going to continue to work this out. So when I put negative 1 plus h into x squared minus 3, you see why function composition from chapter 1, I made sure we do this again. It's going to play a big role in calculus composition. So then we work this out. And you remember, when you square things, you'll probably get 3 terms like this. So, negative 1 times negative 1. Negative 1h, negative 1h, h squared. Okay, and I group any like terms possible. I put that in a bracket so you know where it came from. It's actually a good habit to always put polynomials when you multiply them out in a bracket, because if they're the second thing and you're subtracting, you're bound to make a mistake if you don't think in brackets.
Just use the x and y together and put it into the main function.
Okay, I better slow down. You said added, and I think you're using it non-mathematically. Let me see. You substituted in this for f of x, yes. I know what you meant by added, but I want to make sure you weren't talking mathematically. Yeah, okay. So yes. Subbed it in for x squared at that position. For the function, yeah, for negative 1 plus h squared. Here's what we work it out. Okay, this is my y coordinate though, once I group it all together. Oh, you guys like putting square things first, I bet, so h squared minus 2h minus 2. You don't get faster than that guy. Okay, anyways. So we got an x and a y, and you might feel uncomfortable. It's not just a plain old number like 17, but it's an expression that we can use. So then what? Slope formula. Because, how do we evaluate slope of a tangent line without a chart? Well, we still use the slope formula, so I'm going to write it out explicitly. Now, whether we want to use, just a second here, going back to here, you know, this is the way you guys are used to seeing it, right? Y minus y over x minus x. It's no different if we say the function value at q and p, right? I'll do it with y minus y. Okay? Now, my second point is going to be q, so I'm going to plug in for y, 2. H squared minus 2h minus 2. Right? I'm using red so you know where it came from, right? Because it'll work above. The point P's y value is negative 2, so minus negative 2 all over x2. What was my x for the q point? Negative 1 plus h. Oh yeah, that's what it was. Subtracting. The original point P had an x value of negative 1. I slid up to see where it was. Yep, it was. Okay. All I've done is substituted into this form. Now what? Well, let's just do some algebra, arithmetic, whatever you want to, stuff like this, group-like terms on the numerator and denominator. H squared has nothing to group with. I'm going to drop the color scheme too. So it's just h squared. Minus 2h, nothing else to group with. Minus 2 minus negative 2, so that zeroes out. Negative 1 minus plus, so minus negative 1, it's positive 1, so zeroes out. Now, what were we saying that we're going to let this h equal, because it's coming in tight? 0. But you can't put 0 in here, right? Can't do that. So what do we do when we want to know what it would be if you could let it equal 0? We limit it, right? What does it seem to be as, because philosophically it's not exactly plugging this in. So to find this slope, we got to use a limit. So I'm now going to say the slope, I'm changing this up a bit, is the limit of h approaching 0 for this expression. Hey, you guys know a few tricks with limits. If you get 0 over 0, that's called indeterminate form. What do? Manipulate it. Hopefully it comes out. Can you back to the top? Darn tootin'. Or some people just think right from here, I distribute the division to each thing. Either way works. If it's mathematically sound, use it. Hey, did you notice something? And nobody lost marks, because that's really why I wanted those questions the other day, the limit questions. So when you gave them, when do you drop this limit notation? The minute you sub in for h in this case. Before that, if you have little stars beside their limit notation, it's because use the limit notation in front of the expression until you put in whatever value you're substituting. Okay, so the h is canceled. I can now do this limit, 0 minus 2, right? I'll write it out as 0 minus 2, but I think you could just jump to it. Does this give us the same answer the chart did? Yep. You'll get better at it, and there's some shortcuts and tricks. This will be a way quicker method than ever using a chart. Okay? Now, I know we're kind of... I'm going to stop the recording here just a second.